Now let's do one example under Clausius inequality. How do you remember or understand Clausius inequality? It is just second law of thermodynamics expressed in mathematical terms. So now here we have a power cycle. QH is 1000 kilojoule and the temperature is 500 K. You convert it to mechanical work, and W cycle is 410 kilojoule. Second law tells us you have to lose some heat, which is QC, and that is 590 kilojoules. TC, the environment temperature, is 300 K. So this is your design of an engine. Our question is your design possible or not? So we actually did this problem before, if you can remember. How did we decide if your system is possible or not? We checked your design against first law first, and then we check your design against second law. Your design cannot violate any of those two, otherwise your design won't be possible. So now let's check again first law too. First law first. What is first law? First law is conservation of energy. Total energy going in must be equal to total energy leaving. Total energy going in is 1000 kilojoules, QH. Total energy leaving is W cycle and QC, so that's 410 plus 590. In total, that's 1000. So 1000 goes in, 1000 comes out. There's nothing wrong with that. So this design does not violate first law. So first law is satisfied. Next, let's check if we can satisfy the second law. The last time we checked was to compare eta with eta max. We compare the actual efficiency eta, we also find out eta max, the maximum efficiency. And then the solution was our actual efficiency eta is even higher than eta max, which is obviously not possible. Then we said this design is not true. Today we can check second law again, but this time we use Clausius inequality and see if that will give us the same conclusion. So now we will write down Clausius inequality first. Integral delta Q over T over the whole boundary, right hand side negative sigma cycle. Okay, so now let's do this integration. This integration needs to happen over the whole boundary, So now let's take a look. What is my boundary? My boundary is a box. So we have the top surface, bottom surface, left surface, and right surface. So in order for us to integrate the whole boundary, we just separate the whole boundary into four parts. The first one is the top surface. And then the second one is the bottom surface. And then we have the left and the right. Okay, so now let's take a look at left surface and the right surface. On the left surface, which is this one, do we have heat transfer on the left surface? There's no heat transfer. So what's going to happen is Q is equal to 0. If Q is equal to 0, this term goes to 0. And now let's take a look at the right surface. If we take a look at the right surface, which is here, do we have heat transfer? We have work, but we do not have heat transfer on the right surface. So on the right surface, Q is also 0. If Q is equal to 0, then this term goes to 0. And now, top surface and bottom surface, do we have heat transfer? Yes, we have QH and QC. So now they're not equal to 0. We have to keep them. Okay, so now let's continue with this equation. What's going to happen to the temperature on the top surface? What is the temperature here on the top surface? Temperature on the top surface is TH, which is 500 K. And now you can see this temperature is constant. If this temperature is constant, what you can do is to pull it out. So it becomes 1 over TH. And what is left is integral top surface delta Q. And then we can do the same thing for the second term. What is the temperature on the bottom surface? The temperature on the bottom surface is Tc 300 K, which is a constant. Since it is a constant, you can pull it out again. So 1 over T cold. And then what is left is integral over the bottom surface multiplied by delta Q. And now let's continue. Integral delta. What is delta? You can just think of delta as derivative if you prefer. So what we have is integral and derivative. They will cancel each other. So what is left is just a q on the top surface. And a q on the top surface we call QH. First term just becomes QH over TH. We do the same thing for the second term. Integral cancels derivative, so what is left is q on the bottom surface we call QC over TC. So this is the equation. Do we have all four numbers? Yes, we do. QH is equal to 1000 kilojoule. And QH goes into the system, so your system gains heat. If your system gains heat, you should plug in a positive QH. So that's 1000 kilojoule. Multiply this number by 1000 to convert it to SI unit, which is joule. Divided by T hot. T hot is given, which is 500K. 500K SI unit, nothing we need to do, plus QC. And what is QC? QC is given as 590 kilojoule, but QC comes out of the system. If the system loses heat, you should have this Q as a negative number. So we plug in negative 590 multiplied by 1000 to convert kilojoule to joule. Divided by temperature. What is temperature? Tc is given as 300K. Okay, and I will make a note here so you don't forget to plug in the negative number. Okay, so now you use your calculator. Your solution is 33 joule per Kelvin. That is the unit. And don't forget, that's our left-hand side. What is the right-hand side? Right-hand side is negative sigma cycle. So right-hand side is negative sigma cycle. So now we have left-hand side equal to right-hand side. Left-hand side is 33 joule per Kelvin. Right-hand side is negative sigma cycle. So finally, sigma cycle is equal to negative 33 joule per kilogram. And is that possible? Let's go back. If your sigma is negative, what does it mean? That means your design is impossible. Just like your age. If your age is becoming smaller, that means it's not possible. So our conclusion is your design is wrong. It's impossible because it violates second law of thermodynamics. So just like what we did before, we compared eta with eta max, and eta because eta was even bigger than eta max, so our conclusion was your design is wrong. So now we do the same thing, but using a different method. By Clausius inequality, our solution is sigma is a negative number, which is never possible. So your design is wrong again. Same conclusion, different method. It violates second law. So now we can go back, we say, okay, you violate second law, and that's gonna be wrong. Your design is impossible. Okay, so that is the example.